What specific problem does your method aim to solve, particularly in the context of open-weight models, and how does this relate to existing concerns within the field?
Our method aims to address the problem of mitigating harmful uses of advanced open-weight language models, LLMs, by preventing them from acquiring biothreat proxy knowledge during pre-training. This is particularly relevant given the increasing security risks associated with open-weight models, as highlighted by concerns from organizations like Google DeepMind and Anthropic regarding their potential to assist in harmful activities, such as the development of chemical and biological weapons. We introduce a multi-stage data filtering pipeline that effectively removes documents containing proxy biothreat knowledge from the training dataset, achieving state-of-the-art tamper resistance without degrading unrelated capabilities. This approach is crucial as open-weight models can be modified arbitrarily by downstream actors, making them vulnerable to misuse. By focusing on pre-training data filtering, we provide a proactive strategy to enhance the safety and robustness of open-weight models against both adversarial and non-adversarial tampering threats.
Can you explain how your proposed method works? Please provide a detailed, step-by-step breakdown of the multi-stage data filtering pipeline you introduced for mitigating biothreat proxy knowledge.
Our proposed method for mitigating biothreat proxy knowledge involves a multi-stage data filtering pipeline designed to efficiently identify and remove harmful content from training datasets. The first stage utilizes a keyword blocklist filter, where we generate a list of key terms from a specific dataset and process each document to check for the presence of 2 or more terms from this blocklist. Documents that meet this criterion are escalated to the second stage. In the second stage, we employ a fine-tuned modern BERT classifier, which reviews the escalated documents to further reduce false positives by distinguishing between proxy documents and benign content. This two-stage approach allows us to filter out approximately 8.42% of pre-training documents and 9.36% of annealing documents while maintaining a high level of efficiency, using less than 1% of the total training flops. Overall, this pipeline effectively prevents the acquisition of biothreat proxy knowledge without degrading unrelated capabilities.
Could you provide a specific example or a hypothetical scenario that illustrates the functioning of your filtering pipeline? How would it process a document with biothreat proxy knowledge?
The filtering pipeline we developed consists of a multi-stage process designed to identify and remove documents containing biothreat proxy knowledge from the training dataset. For instance, if a document is processed and contains 2 or more terms from our predefined keyword blocklist, it is escalated to the next stage, where a modern BERT classifier is employed to further assess its content. This classifier, fine-tuned on expert-labeled examples, evaluates the document to determine if it indeed contains biothreat proxy knowledge. If the classifier confirms the presence of such knowledge, the document is filtered out of the training dataset. This efficient approach ensures that less than 1% of the total training flops are used, while effectively preventing the model from acquiring harmful knowledge without degrading its unrelated capabilities.
What are the key advantages of your method in terms of efficiency and effectiveness compared to previous approaches? How does it maintain unrelated capabilities while implementing these safeguards?
Our method introduces an efficient multi-stage data filtering pipeline that accounts for less than 1% of total training flops, significantly enhancing the efficiency of the training process compared to previous approaches. This filtering technique effectively prevents biothreat proxy capabilities without degrading unrelated capabilities, as evidenced by our evaluations showing no apparent net degradation in non-bio capabilities. Specifically, we demonstrate that our filtered models achieve state-of-the-art tamper resistance for up to 10,000 steps of adversarial fine-tuning, outperforming existing post-training safeguards by more than an order of magnitude. Additionally, our approach allows for the retention of general knowledge by focusing on the removal of specific harmful content, thus ensuring that the model remains robust in unrelated domains. Overall, our findings suggest that careful curation of pre-training data can yield significant safety improvements while preserving the model's overall functionality.
How did you validate the effectiveness of your method? What datasets, benchmarks, and specific metrics did you utilize to assess the success of your data filtering approach?
To validate the effectiveness of our data filtering method, we utilized the WMDP Bio benchmark, which is a 4-way multiple-choice question-answering MCQA evaluation designed to assess biothreat-related knowledge. We specifically focused on 2 curated subsets of this benchmark: WMDP Bio Robust MCQA, which excludes samples easily guessed by other LLMs, and WMDP Bio Verified Close, which evaluates the model's ability to predict answers without seeing all choices. Additionally, we employed standard question-answering benchmarks such as MMLU, Pika, and Lambda to measure general capabilities and ensure that unrelated knowledge remained unaffected by the filtering process. Our results indicated that data filtering significantly inhibited biothreat, proxy knowledge acquisition, while incurring minimal costs and no apparent degradation in non-bio capabilities. We also assessed the robustness of our models against input space adversarial attacks, demonstrating that our filtering approach outperformed baseline models in this regard.
What were the most significant results of your experiments with the proposed method, particularly in terms of its performance against adversarial fine-tuning and input space attacks?
The most significant results of our experiments with the proposed method, which involved training data filtering, demonstrated substantial improvements in tamper-resistance against adversarial fine-tuning and input space attacks. Specifically, our filtered models exhibited state-of-the-art tamper-resistance for up to 10,000 steps and 300 million tokens of adversarial fine-tuning, outperforming post-training baselines by more than an order of magnitude. Additionally, data filtering showed superior performance against input space attacks, particularly in the context of GCGU attacks, where it outperformed circuit-breaking methods on average. However, while filtering improved robustness against these attacks, it was less effective against few-shot attacks compared to circuit-breaking techniques. Overall, our findings indicate that training data filtering is a powerful tool for enhancing the safety of open-weight language models against various tampering threats.